Okay, thank you, everybody. And thank you to the organisers for bringing us all here. It is lovely. Right, so this is a talk about using ADS-CFT to try to understand non-supersymmetric gauge theories. And that's been done in the past, and I want to try and convince you that there have been some new developments that are at least of some interest, I hope. Okay, so I'm going to talk about two sort of bits of new work. One is with Johanna Erdmenger and Werner Porod in Würzburg, as well as with my ex-student Kostas Regatos, who is now in Boulder. So that's the work on multi-representation theories. And then I shall at the end talk about a domain wall mechanism for generating chiral matter, which I've done with my student in Southampton, Jack Mitchell. Okay, so let me begin by just reviewing sort of the olden days with people using ADS-CFT to describe mass generation, basically, in QCD. And, well, there are many things, of course, that are remarkable about ADS-CFT, but one of them which really struck me all the way back when we got the first paper from Ed is that this has nothing to do, really, with conformal symmetry or supersymmetry. A black hole geometry we immediately knew was describing a finite temperature theory. And that means that this formalism has in it potentially all of the dynamics that you need to describe theories, if not QCD, at least like QCD. So back in 2003, Johanna and I tried to push things in this direction. We came up with a D3, D7 construction. So here, the strings between the D3 and the D7 are introducing quarks into the ADS-CFT correspondence. And what we basically showed back then is that if you do something in the geometry which puts a repulsion in from the point of view of the D7 brane, so you might have some running dilaton, which means that the D7 doesn't want to go into this central area, then you would get these sort of bent configurations where in the infrared the quarks have a mass, whilst out in the UV the asymptotics have a massless quark. So that's chiral symmetry breaking in the joule. Okay, and fairly shortly after that, we also got the Sakai-Sugimoto mechanism of where you have chiral fermions on separated branes and anti-branes, and then the famous U-shaped configurations where these branes join, and that was again, that joining was assumed to have something to do with chiral symmetry breaking. Okay, around the same time, there was the ADS-QCD model, a very, very simplistic model with just a hard wall on ADS. And this action is basically just the action, the dBi action of the D7 branes, with X the field that describes the position of the D7 branes. And these authors developed fluctuation technology down to the point where you could actually make some predictions for QCD in these models. Okay, and those came out reasonably well. I'm not going to review all that fluctuation theory because probably people know it pretty well. The conclusion from this is that the probe limit for a D7 brane, perhaps, or some other brane, and its dBi action actually contain an awful lot of the physics of quarks. Now, this really all gelled together for me in 2011 as the result of the work of Jarvin and Karitzis, that all of these models, in a sense, become the same model. And that's because we came to realize that what's happening in all of these theories is that there's a scalar field, the position of a brane, or just the X field in ADS-QCD. And the point is that the thing that connects these descriptions is that these theories have a running of the anomalous dimension of the quark operator. So let me just show you that in detail. So here's just the simplistic action of the basic ADS-QCD. And you can see that you've got a scalar with mass squared equal to -3, which if you stick it into the mass dimension formula tells you that you are indeed describing a dimension 1 mass and a dimension 3 quark condensate. Now, if you do anything in one of those brane constructions, and the simplest thing you can do is, for example, to switch on a magnetic field on the surface of the brane, so associated with U1 baryon number, you get an effective dilaton factor in the dBi action, which is this. You can just expand that, of course, at large X, or small x even, and you, of course, you get an x squared term. So this is something that comes in, it's R dependent, and it changes the mass of this field. The result is that as you go into the center of the space, into this region here where the D7 brane was bending away, what is going on is that there is a BF bound violation that the mass squared has gone through -4, and that's the instability to chiral symmetry breaking. In terms of the dimensions of the operator, this corresponds to when the anomalous dimension of the quark condensate falls to 1. So all of these theories are basically the same. They have these properties. So in the Sakai Sugimoto models, these are the tachyon field that plays the same role. All right, so you're a better person than me if you can see that and not immediately go, oh well, I think I'll just stick in whatever I fancy for this running here. So I imagine that might come from the fact that I've finally got the actual QCD joule, and I've got the geometry, and now I feed it into a probe brane, and all it does for me is to give me this running of this mass. But I, roughly speaking, know the running of the anomalous dimension of the quark condensate in QCD. You can do it at 1 or 2 loop in perturbation theory. It makes alpha run, and then gamma is just a factor times alpha. So if you want, you can feed that into the formula which links the dimension to the mass, and you can actually see how the change in the mass apparently should look for QCD. Okay, and you can see here that this would be, when it goes through -1 here, would be where there's a BF bound. And now you stick this into that simple basic ADS QCD model, and you get these sort of D7 brane-like embedding functions describing the situation. Okay, and this gives you a dynamical model with the chiral symmetry breaking included, and again, you can play ADS QCD games and try and make some predictions. Actually, they don't look as good as in the original model, because here we're actually predicting the dynamics. In the original model, they fixed the condensate as part of the fit, which makes things look a little bit better. All right, and you can see, I mean, it works not disastrously, reasonably well, gives you the right sort of pattern. If you want to go beyond doing reasonably well, I have long advocated that the correct thing to do is to borrow from our lattice gauge theory friends' idea of perfection and perfect actions. So here, you just have to accept that there is not a weakly coupled gravitational joule of the weak coupled UV of QCD. And so what you should do is to put in a cutoff on your gravity theory at probably around 3 GeV or so, where QCD enters strong coupling. You then hope that there's maybe an order of magnitude between that scale and the scale where confinement and chiral symmetry breaking occurs down at maybe 300 MeV or so. Okay, if you do this, you now have to match at this UV scale to the physics above that scale. And that means including higher dimension operators. And over the last few years, of course, we've come to understand how to include high dimension operators using Witten's multi-trace prescription. So, for example, if you want to include a Nambu-Jonah-Lacinio 4 quark operator such as this, then the observation is basically that when the quarks condense, you get an effective mass term out of this interaction relating M and Q bar Q. And so, of course, the mass and the condensate are the two constants that you get from the UV profile of these solutions. And now what you can do is just reinterpret those solutions, but with this relationship between C and M. In other words, you can just go to one of these guys and you can treat it as though it's actually a theory with a massless quark, but the mass and condensate are induced by the NJL interaction, and you can just read off G squared from them. Okay, using that sort of technology, you can go into the fluctuation theory, and you can include a 4 quark operator, one that affects the vector meson, one affects the axial vector meson, and even if you want, you can put fermions in the bulk to describe the proton, and then play the same game with those. And now you can see that you can get a perfect looking spectrum by fixing these higher dimension operators. Well, that's not doing anything. You've then got to make some predictions. And, okay, so if you start, for example, to look at the excited states of some of these things, you can see that relative to here, where there was sort of 20% or more errors, you actually bring those errors down to below 10%. So it does suggest that you can effectively improve the model. I should say also that the fact that it's working on these excited states is probably showing that you're also with these higher dimension operators including some stringy corrections to the basic ADS CFT configuration, which is presumably the right way in which you should be approaching QCD. All right, so that is a review of sort of what has happened and where ADS QCD lies. So what I want to do now is to talk about multi-representation theories. And the main reason for that is that in the last few years, there is now lattice data for some of these theories, and that makes it interesting to go back and see if we can reproduce that data. Now look, traditionally, you would say if you have a quark in a dimension higher than the fundamental, then as you scale with NC, it's going to grow like NC squared or higher. You've got to include that in the back reaction of the theory, and therefore you wouldn't think of doing this sort of probe ADS QCD thing. On the other hand, what we've sort of learned over the years is that all the back reaction and the background geometry is doing for you is in a sense just feeding in what the correct anomalous dimension is for that quark operator. So we could play the game, therefore, that I've already been playing, of looking at just something that describes the quark-anti-quark operator, and just put in by hand what we make as our guess from perturbation theory of the running of the anomalous dimension. Okay, as I say, the reason to do this now is because there is data. So the lattice groups were actually inspired by composite Higgs models. So these are very quickly models where there's chiral symmetry breaking. You get 4 Goldstone bosons as a result. You dress them up so that they look like the Higgs. If you want to also give the top its mass, you need some baryons that the top can mix with. Personally, I find these models pretty ugly. But they inspired the lattice groups to go and look at these theories. And so just as a purely field theoretic idea, we can go and see if we can model these. So for example, there is data on an SP4 gauge theory with 4 viol fermions in the fundamental and 6 viol fermions in the 2-index antisymmetric representation. So if we just use perturbation theory to plot what the effective running of the mass of the scalar in the bulk would be, we get the blue for the fundamental representation and the orange for the A2 representation, except that presumably when this orange one is the first guy to condense because it violates the BF bound, at that point we should integrate it out of the running, and then the blue running becomes much stronger below that scale. And depending on precisely what assumptions you make in here, you can get, red, blue, or orange type D7 embedding functions out. We also are going to compare to quenched data, so that's where you just remove the fermions from the running, and then it's just run by the glue, and so you get these purple and yellow examples. Okay, so let's immediately just go to some data from 2019, the lattice. So this is this exact theory, but quenched. So we just go in and we run this model. So we have 2 of these X fields, one to describe the quark condensates in each of the 2 fermionic sectors. You have to set the scale. So we do that with the vector in the A2 sector. And then you get a bunch of predictions. And okay, so you look down that list, probably it's a bit hard to take it all in one go, but what you see is that, again, just like ADS QCD, it gives you a pretty good stab at what this theory looks like. It's getting, the rough pattern of these things right, even where the exact numbers are not correct. It also correctly predicts or agrees with the lattice that the higher dimension representation condenses first, and then the fermionic sector later. Okay, so of course, given these 2, which one are you going to believe? You're going to believe the lattice data. But the thing that's important to understand is that these guys have sort of done all they can with their money and their resource, and they're still in the quenched theory. So you might want to know, or indeed the model builders might want to know, how big a difference are you going to get when you unquench the matter? And that's something that these guys really are struggling to do, but we can just do rather trivially by changing the running. And so that then takes you over to this column here, where you can see that there are of order 10, maybe 15% changes in quantities. And so we think that we're helping to support the lattice community by saying how good their results are likely to be for the real theories that they're looking at. There's another theory, which is the SU4 gauge theory, with 3 Dirac fermions in the fundamental and 5 Weyl fermions in the 2-index antisymmetric representation. This has been studied by these gentlemen on the lattice, and they've done something that's unquenched, which is good news. Unfortunately, though, they can only unquench when they get the fermionic content slightly wrong. So they just have 4 2-index antisymmetric guys and 2 flavors in the fundamental. But then they can just go and they give us some predictions. So again, we can run our ADS QCD type model, fixing again that vector state. And again, you can see that it's not perfect, but we get somehow roughly the right pattern of what's going on in that state. And again, the question that the model builders will have here is, well, if I go from this to the real theory with the real matter representations, how much do things change? And that's something that we're trying to tell them the answer to by then working out these columns. I should say again that the changes are actually pretty small, which is encouraging, with one exception, which is the sigma or scalar sector, where it really depends very carefully in these holographic models on the running rate. So the more fermions you put into those theories, the slower the running and the lighter that scalar is, as it sort of becomes perhaps a little bit dilatonic. It also made us just wonder how big we could make the gap between the condensation scales of 2 flavors. And if you just take the naive perturbation theory results and the gamma equals 1 criteria, we actually discovered that there are some theories with quite remarkable gaps. So, for example, if you take an SU3 gauge theory with 10 fundamental fermions and 1 Weyl adjoint gaugino, if you like, you can actually get a gap of 20 between the condensation scales of the 2 representations. And given that the confinement scale of the theory is presumably in the QCD-like region of low energy below the second condensation, that suggests these theories may have big gaps between confinement and chiral symmetry breaking. So it'd be really interesting to study those on the lattice. Unfortunately, they're quite walking theories, so they're hard for the lattice to study. All right, at this point, I have reduced string theory to a low-energy infrared effective theory, and people in the audience are getting grumpy at me. So let me go back and, to finish off at the end, do something different, which is to talk about a top-down construction to try and understand chiral fermions, how you put chiral fermions into a joule. And again, I'm inspired by the lattice, where since 1992, David Kaplan taught them that the way that they could get chiral fermions on the lattice was to use the domain wall fermion trick. So the basic idea is that you put the fermions in one higher dimension than you want. In that dimension, you let the mass of the fermions have this step-like function, and where the domain wall lives on where it's switching sign, this is where he showed that you can get left-handed or right-handed chiral fermions localized. Okay, so we wondered whether we could get this going in holography, and so we started off in the D3 probe D7 system because it's sort of the canonical system. So that means here we're starting in 3+1 dimensions, and then we're going to reduce to 2+1 dimensions. So that's not formally chiral fermions, but the 4-dimensional spinner still splits apart into 2 pieces, which are localized at different domain walls. So we started by doing this in the linearized approximation and just building, using Fourier analysis, these sort of step functions in the mass described by the field on the surface of the brain. And then you can just extend that into the bulk by solving the equations, and you get solutions that look like this. So a sort of trough. So the interesting question is, where is the domain wall? Where it's presumably where m equals 0. And if you look down from on above at where that is, then you get these sorts of configurations here. U-shaped configurations where the two domain walls come together and join, and it immediately makes you think Sakai Sugimoto. Now, in the large mass limit, so that's where I take this mass here and this mass here to infinity, then the field which comes into the dBi action just by its derivative is basically, the derivative is zero everywhere except on these domain walls where it's infinite. So if you make an ansatz that it's an infinite delta function with the appropriate Jacobian factor, and you substitute that into the action, you can get an action for where that domain wall lies in the space. And remarkably, it turns out to be exactly the same action as if you put a probe D5 anti-D5 brane into ADS5. And that's presumably because both systems have light quarks on their, or massless quarks on their surface that are interacting with the same gauge dynamics and therefore generating the same mass gap. Now, the reason that we think our system is better is that in those brane-anti-brane systems, the quark condensate is actually a non-local thing, an owl, as Offeraroni and collaborators called it, where you have a left-handed quark here, a right-handed quark here, and an open Wilson line between them. However, if you go down to the infrared, then of course this Wilson line shrinks to a point, and then it becomes a local operator in the infrared. But these theories already have a field, the position of the D7 brane, which describes the local quark condensate. And so our supposition was that down at the tip here, these guys and this field would source each other, and therefore we should be able to look for fluctuations of the D7 brane just on this U-shape, so restricting to the loci of the domain wall, and those should give us an explicit description of the chiral condensate and mass. So we insert this basically into the action to reduce the theory down onto the U, and then indeed you can just see by inspection that a UI equals a constant is the minimum action solution, and the natural thing is to set that constant equal to the infrared mass gap. So that suggests that these theories, in fact, have chiral symmetry breaking, but purely through a hard mass, and that hard mass scales as 1 over the width of the configurations. To see chiral symmetry breaking, you need to do something in the infrared, so you might introduce a magnetic field, and then you get an effective dilaton, this H thing, which looks like 1 plus 1 over rho to the 4th. Actually, that turns out not to be strong enough, so just heuristically, we've put a Q in there, and if you make Q a bit bigger, then what happens is that the U's come in, as you separate the domain walls, they go deeper into ADS, but eventually they pile up at some infrared point. If you then go and you solve for these fields on the loci of the domain walls, you get these sorts of configurations which show classic chiral symmetry breaking behavior. And indeed, if you calculate the pion mass, you get a Gelman-Oakes-Renner relationship where the pion mass squared is proportional to the quark mass at low energy. And then at high quark mass, it goes off to being m pi squared, goes like mq squared. So the whole interpretation seems to be very nice and consistent. That was all going to a 2 plus 1 dimensional theory. So we've come up with a construction that takes us to 3 plus 1 dimensions. It's the D7 probe system. Now, actually, Myers and Thompson showed that the UV of that is a little bit confusing because the fluctuations are not normalizable. However, we compactify one direction, and then we put a domain wall, so that's the 5 direction, that introduces confinement, and then we put a domain wall in this X4 direction so that we get real chiral quarks living on our 3 plus 1 dimensional domain walls. And now everything seems to be fine. We're just looking at the infrared of the theory, so I guess it's managed to correct itself. And again, we get this pile up of these domain wall configurations where they join. We get the surface field showing chiral symmetry breaking, and we get a Gelman-Oakes-Renner relation. You can even go all the way and make ADS QCD type predictions with this setup, which it isn't quite as good as basic ADS QCD, but it almost is. Coming out soon will be a paper about the thermal transitions. I don't quite have time, but they're actually more interesting than you might think, because you now have the ability to really identify which theories have the same UV parameters. All right, so let me come to my conclusion. I think holographic QCD is still an interesting playground and there's still work to be done here. Holography does seem to be a remarkably simple way to get ballpark answers that, sit reasonably well with many, many hours of lattice work. I've suggested that you can treat it as effective theory and systematically improve things a la perfect actions. There's new lattice work that we're connecting to, new ideas that might come out of all of this. And finally, the domain wall fermions, a new top-down direction for making ADS QCD models. But really what we're hoping is to go on and construct more exotic chiral gauge theories using this construction. I will stop there.
Yeah, thank you much for your talk. We have time for a few questions. So let me start with a question. Can you go back to the slide where you showed this Gell-Mann-Oaks-Renner relation? I was not really sure whether in the beginning it's really linear or whether this is still quadratic. So because the blue dots are a bit below this red line and then above the red line. So
yeah, so I mean it's quite hard to do the numerics because there's this pile-up point where things become singular. That's the best we've managed. I mean, it's clearly not going like m pi squared goes like mq squared. So as good as I can do for you.
Further questions?
In theories with mixed representation fermions, for example, in QCD with one adjoint and multiple fundamental representation fermion, you can do something quite interesting. You said this is an example of separation of scales between confined and chiral symmetry. But if you do consider not the thermal partition function, but a more exotic form of partition function, which is graded by fermion number modulo 2, which is a symmetry in this example, also use some global symmetries. This theory turns out to be very interesting because you can go from large R3 times S1 to arbitrarily small R3 cross S1 continuously. So without a phase transition. So you can realize, for example, chiral symmetry breaking at arbitrarily weak coupling.
Yeah, so I'm aware of this, and there's a big discussions between different communities, including the lattice ones, as to whether there are these separations or not. This is an unbelievably naive, perturbative analysis just with this gamma equals 1 criteria. I mean, I think, all I'm really trying to highlight here is we should get to the bottom of this. So I encourage the lattice people to really go out there and understand if these theories can have gaps or not. Because it may be that what happens is that the act of chiral symmetry breaking happening somehow triggers confinement immediately in some way, and then it would bring everything to one scale. Yeah. So, I'm model building in a sense here.
So for that thing, the relation between the confined and chiral symmetry breaking scales, I think you can also write down prove an inequality based on mixed anomalies. It exists in the literature now from several years ago.
Well, okay. I mean, of course, if you put in NJL interactions, it's known that you can separate confinement and chiral symmetry breaking.
No. I mean, massless QCD with just adjoint and fundamental fermion. Not a model, not adding anything extra.
Okay, let's talk later.
Okay, further questions? Don't see any raised hands. Yeah, shout at me if you raise your hand. Okay, if that's not the case, then thank you again for your effort.